Welcome to this Esteem How-To video. We'll show how to set up a waveguide port so it can be used as the source in an antenna system. Once the port is created, we also demonstrate how to properly close the region behind the waveguide port. The example displayed here consists of a 1.3 meter parabolic center-fed reflector, a pyramidal feed horn, and 3 struts. We consider a KU band configuration at 12 GHz. The geometry is defined through CAD files and box objects, and we have collected these in several so-called scatterer clusters. There is one cluster for the horn, one for the struts, one for the combined horn and reflector, and finally one with all components included. We have also set up the frequency and method of moment objects and defined a number of coordinate systems. The one coordinate system we'll use explicitly in this video is shown at the input throat to the horn. In addition to the geometrical objects, we can also display the MOM mesh by opening the 3D view settings dialog and toggle the MOM mesh on. The MOM mesh looks good and useful for the analysis we'd like to perform here. So with the mesh in place, we're ready to excite the structure with, in principle, any kind of source. But in this case, we'll excite it with a mode from a rectangular waveguide via the input port on the right side of the horn. To do so, we need to create a couple of objects needed to define the mode, the port, as well as the excitation in the MOM analysis. We'll illustrate and explain this in the following. First, we create the object for the exciting mode. This is the so-called TE10 mode of the rectangular waveguide, which is also the fundamental mode of this waveguide. Then we create the object for the expansion settings of the port. These settings are used to couple the waveguide problem behind the port to the MOM problem in front of the port. For the chosen dimensions of the rectangular waveguide, we'll come back to this shortly, only the TE10 mode can propagate at 12 GHz, while all other modes of the waveguide are evanescent, since the next higher order modes have a cutoff frequency at 15.73 GHz. Additionally, the waveguide is approximately 2 wavelengths long, so we don't need to include higher order modes in the port modal expansion settings. Next, we create the rectangular waveguide port. It has a dimension as the input waveguide of the horn, which is a so-called WR75 standard waveguide. The port also refers to the just defined port modal expansion settings. Finally, we create the MOM waveguide excitation, which is the source that we'll use in the method of moment calculations. We use the port and TE10 modes that we just defined, and otherwise we leave the object with the default settings. A final preparation is to add the waveguide port under waveguide ports in the MOM object. We refer to the newly defined waveguide port and place it in the coordinate system at the input to the horn. We place it in the center of this coordinate system, 0, 0, 0, and orient it along the positive z-axis, corresponding to excitation into the horn. After adding the waveguide port in the MOM object, the 3D view updates, and we can see the port as a transparent green plate at the input to the horn. We now have the geometry and associated MOM mesh set up, as well as the port excitation, and we're thus ready to set up commands to perform a calculation. In the Commands tab, we define a getCurrents command with the waveguide excitation object as the source and the MOM object as the target. Similarly, we define a getField command with the MOM object as the source and the predefined cut object as the target. With these commands in place, we submit the job. In the Jobs tab, the log output of the job is shown, and after a short while, a warning pops up. Jobs can run with a warning, but in this case, we manually stop the job to explore this warning and hopefully avoid it. The warning describes that it's generally recommended to close the region behind the waveguide port. That is, there should ideally be a closed perfectly electric conducting PEC region behind a waveguide port. This will, in general, make calculations more accurate, so we will do that here. We return to the geometry and zoom in on the waveguide port. To close the region behind the port in this case, we will add a small semi-open object. This is done by adding a box with the same XY dimensions as the input waveguide and with a length of 10 mm, corresponding approximately to half a wavelength. We remove the Z-max face of the box to make it semi-open. When we press OK, we can see the box in the rightmost side of the 3D view. To include it in the calculation, we add it to the horn scatter cluster called cluster horn. This cluster is included in cluster all, which is the scatter cluster used in the calculations. After including it, the mesh is updated, and we can now see the box in transparent green behind the port. This coloring indicates that it constitutes a closed PEC region, which is precisely what we wanted to achieve. The updated geometry close behind the port is now ready, and we start another calculation. We write a short comment and submit the job. On this standard laptop PC, the analysis will take about 6 minutes. Let's fast forward through this. At the end, we can see that it required 2.2 GB of RAM and took a little less than 6 minutes. So let us now compare two results from this calculation with other results. As a first result, we can see the reflection coefficients in the log output. The value is minus 13.94 dB, and this is for the horn integrated with the reflector and the struts. A relevant comparison of this number is to the reflection coefficient for the horn on its own. Very often the horn will be designed alone, and the reflection coefficient being a key design parameter. But the horn typically has to work in the presence of an antenna and a platform, which, for example, could be a reflector and a struts like we have here. In job 01, we pre-computed an analysis of the horn alone. And in the log output for this job, we see that the reflection coefficient is minus 31.47 dB. So it is much lower for the horn on its own than for the horn integrated with the reflector and struts. Of course, here we're considering a center-fed configuration where the reflection coefficient is very strongly degraded due to the reflector, much more than if it was a less compact and offset design. But nevertheless, with the STEAM, we can quantify the effect of different parts of the antenna geometry and get this information. A second comparison is for the antenna patterns with and without struts. We have pre-computed the results without struts, that is, the horn and the reflector on its own, in job 02. In the Results tab, a plot is shown of the pattern cuts in the two principal planes for the situation without struts. We can compare these to the ones with struts included that we just calculated in job 04. After adding the patterns to the plot, we also just adjust the legends. And then we compare blue and green with black and red respectively. We also display the curve peaks and zoom in on the peaks. Here we see that without the struts, the peak is 39.9 dBi, while with the struts it is 39.1 dBi. So we lose 0.8 dB of peak directivity due to the strut blockage. If we zoom out again, we can also observe that the side lobes for the situation with the struts are somewhat higher than without struts, as could be expected. With STEAM, we can accurately quantify the influence on the radiation pattern from different parts of the antenna geometry and platform, and this is one of the very powerful features of the product. That's the end of our how-to video on setting up and performing antenna analysis with waveguide port excitation in STEAM. I do hope you enjoyed it, and I thank you for watching.